It's not pollution turning the Black Sea turquoise. For a few weeks every year, satellites orbiting 250 miles above Earth photograph the Black Sea, and most of the time it looks exactly the way you'd expect. Dark, almost slate gray, the kind of blue that swallows light instead of throwing it back at you. Then one image comes in different. The whole northwestern coastline is glowing turquoise, not a shade you'd call natural for open water. It looks like someone poured milk and mint into a sea the size of a small country. And here's the part that should bother you. Nothing artificial caused this. No chemical spill, no algae warning on the news. The water itself changed its physics, and it happened almost overnight. So what actually flips a sea from black to bright turquoise in a matter of days? The first guess scientists usually reach for is pollution. Runoff, industrial waste, something dumped upstream that discolors the water. It's a fair guess because it's happened before in other seas, but the chemistry doesn't match. Pollution tends to make water murky, brownish, uneven. This turquoise is smooth, uniform, almost painted from orbit. That's a signature, and signatures usually mean biology, not chemicals. The second guess is a normal algae bloom. Also wrong, or at least not the full story. A typical bloom turns water green because it's packed with chlorophyll, the pigment plants and algae use to catch sunlight. This water isn't green, it's turquoise, bordering on white in the brightest patches. Something else is going on, and it comes down to the shape of the thing living in the water. The real answer is smaller than a grain of sand, and it's covered in armor made of rock. It's a single-celled organism called a coccolithophore. Under a microscope, it looks almost like a snow globe, a tiny sphere wrapped in overlapping plates, and those plates aren't soft tissue. They're built from calcium carbonate, the same mineral that makes up chalk, limestone, and the shells on your kitchen counter. Each plate is called a coccolith, and a single cell can be covered in dozens of them, stacked like scales on a microscopic dragon you'll never see with your own eyes. When conditions line up, warm surface water, strong sunlight, nutrients drifting up from deeper layers, these organisms don't just grow. They explode in number. A bloom like this can involve trillions of individual cells spread across thousands of square miles, and every single one is carrying its own tiny chalk shell. Here's where the color trick happens, and it's pure physics, not biology. Calcium carbonate is reflective, not transparent like most cell membranes, not pigmented like chlorophyll. It bounces light back the way a mirror or a sheet of white paper does, except at a microscopic scale. When trillions of these calcite-covered cells crowd into the surface layer of the sea, they turn the water itself into a diffuse reflector. Sunlight hits the plates, scatters in every direction, and a huge share of it bounces straight back up toward the sky and toward the cameras looking down. Blue light scatters more than red light in general, which is also why open ocean water reads blue to your eyes in the first place. Stack a dense layer of light-scattering mineral plates on top of that natural blue, and you get the exact shade the satellites picked up. A bright, almost luminous turquoise, sometimes fading to milky white in the thickest patches. It's not a pigment, it's trillions of chalk mirrors floating just under the surface. And scientists don't just guess this from orbit. Research ships sail directly into these blooms, pull up water samples, and run them under electron microscopes back on land. That's how they confirm the culprit every time. The water is packed, cell for cell, with the same armored plates. And that's not even the strangest part. These blooms aren't rare accidents. Coccolithophores have been doing this for roughly 200 million years. The White Cliffs of Dover in England are literally built from the fossilized remains of ancient coccolithophore blooms, compressed over millions of years into solid rock. Every time you look at those cliffs, you're looking at the leftover shells of the same kind of bloom that just lit up the Black Sea from space. The organism turning that water turquoise today is, geologically speaking, one of the most successful life forms to ever exist on this planet. The Black Sea isn't even alone in this. The same milky turquoise swirls show up almost every summer in the English Channel and off the coast of Norway, whenever the water warms enough and the light stays strong enough for long enough. Once you know what you're looking for, you start noticing it in satellite footage from all over the world. So this isn't a glitch. It's a rerun of something Earth has been doing for longer than most continents have looked the way they do now. But the bloom isn't just a pretty picture for satellites. It's doing real work you can't see from a photo. Coccolithophores are photosynthetic. They pull carbon dioxide out of the water to build energy, the same basic process as a plant on land. And when they die, a large share of that carbon, locked up inside their calcite shells, sinks to the ocean floor instead of drifting back into the atmosphere. Scientists call this the biological pump, one of the major ways the planet moves carbon out of the air and buries it for thousands, sometimes millions of years. A bloom the size of the one over the Black Sea isn't just changing color. It's quietly shifting how much carbon stays locked underwater instead of floating around as gas. That means the exact event that makes for a striking photo from orbit is also a working piece of the planet's carbon cycle, running in real time, visible from space if you know what you're looking at. Here's the part that ties this back to something bigger than one sea. Coccolithophores sit near the bottom of the ocean food web. Small fish, filter feeders, and shellfish all rely on blooms like this as a food source, and the timing usually lines up with seasonal shifts that entire ecosystems have adapted to over long stretches of time. When a bloom turns up unusually large, unusually early, or unusually intense, marine scientists pay close attention, because it can be an early signal of shifting water temperature or nutrient flow rippling outward to everything living above it. And there's a real irony buried in all of this. The same mineral shell that makes coccolithophores glow turquoise from orbit also makes them fragile. As ocean water absorbs more carbon dioxide, it becomes slightly more acidic, and calcium carbonate is sensitive to acidity. Research on these organisms has found that shifts in ocean chemistry can affect how well they build their plates in the first place. So the very structure responsible for one of the most visually dramatic natural events you can see from space is also one of the more chemically delicate structures in the ocean. Think about what that actually means. An organism thinner than a human hair, wrapped in microscopic chalk armor, is doing three things at once: turning an entire sea a different color visible from a satellite 250 miles up, feeding a chunk of the marine food web underneath it, and quietly moving carbon from the air into the seafloor for the next several million years. None of that shows up when you first glance at the photo. From orbit, it just looks like a striking swirl of turquoise against dark water, the kind of image that gets passed around because it looks unreal. But nothing about it is artificial, and nothing about it is random. It's the visible result of trillions of individual organisms, each one running the same basic biological process life on Earth has been running since long before anything with eyes existed to look up and wonder about it. That's the real reason this image is worth stopping on. It's not a filter, and it's not a warning sign of contamination. It's one of the oldest tricks life on this planet knows. Mineral armor turned mirror, playing out at a scale big enough to be seen from space. Send this to someone who thinks every ocean color change means pollution. And the next time you hear pollution blamed for the Black Sea turning turquoise, you'll know exactly what's floating just under the surface.